Lesson 7 is called exponential functions, and exponential functions can represent a ton of different real life situations, so that's where we're going to start. So introduction to exponential functions, our first problem is you start with $1 in your savings account, and each day you double the amount in your account. Fill in the table to show your savings after 6 days. So that first spot on the table is already filled in for us. It's saying like on day 0 we have $1 because that's where we're starting, and then it says that each day we are going to double the amount in our account. So if I start with $1 and then I double it, that means I'm multiplying it by 2. So double means multiply by 2. So on day 1, I would have $2. And then on day 2, I would double my $2 into $4. On day 3, I would double my $4 into $8. On day 4, I would double my $8 into $16. On day 5, I would double my $16 into $32. And then on day 6, I would double my $32 into $64. So even though we only started with $1 in our savings account and we weren't really growing it that quickly at first, it just went from 1 to 2 to 4, it doesn't seem like we're saving a lot. But if we're continuing to double the amount in our account each day, it eventually starts to grow really quickly. We got up to $64 in 6 days. And you can imagine if we kept going from there, day 7 would be $128. It begins growing really fast, and that's because this is an example of exponential growth, which means it's something that grows at an exponential rate, which usually means pretty quickly. It can either be growing really quickly or kind of decaying really quickly. Okay, so we are going to get into kind of what the graph of this would look like, but before we do, I want to write the rule, which is kind of the function form of this situation. So if we think about where we started with $1, and then to get to each next day, I was multiplying by 2. So I multiplied by 2 there, multiplied by 2 there, multiplied by 2 each time to double. So notice on day 1, I had multiplied by 1, 2. By the time I got to day 2, I had multiplied by 2 2s. By the time I got to day 3, I multiplied by 3 2s. And then by the time I got to day 4, I had multiplied by 4 2s. So we have a way of writing multiplication of the same number over and over again, and that's with exponents. So for my rule, I'm going to incorporate exponents. So I'll say f of x equals, and I started with that $1, and then after that, I was multiplying by 2 consecutively depending on the day. So times 2, and then the amount of 2's that I multiplied together changed again by the day number. So day 1 was 1 2, day 2 was 2 2's, day 3 was 3 2's, day 4 was 4 2's. So I'm going to say 2 to the x power because that number is changing, and that x power is going to end up being the day number. So we're going to get into writing rules a lot more than just this, but I wanted to give you a quick example. And then it's also important to be able to identify what an exponential function looks like on a graph, because we talked about how it grows really quickly, but it's nice to see a visual of that. So on a graph, this table would look like this. So you can see it kind of starts off a little bit slow, a little bit flat, and then it shoots up and it starts to get really, really steep. And the steeper the line, the more money you are saving, the more quickly you are saving it. So you can see as it continues to go to the right, it's getting steeper and steeper, meaning it's growing at a quicker rate. Okay, so this is an example of exponential growth, when you are growing something very quickly. Okay, so for the second example, you have a 128-ounce bag of chips. Each day you eat half the chips left in the bag. Fill in the table to show the amount of chips you have left after 6 days. So on day 0, that's the first day, or not even the first day. It's when you first get the bag. So you have 128 ounces of chips in the bag. And then on day 1, you eat half of that. So if we eat half of that, we would have to either divide it by 2 or multiply by 1/2. Because remember, if you hear the word of in math, it means multiply. So half of 128 would mean multiplying by 1/2, which is the same thing as dividing by 2. So 128 divided by 2 would be 64. And then on day 2, you eat half of that 64. So half of 64 is the same thing as 64 divided by 2. It's 32. Day 3, you eat half of the 32. So half of 32 is 16. Day 4, you eat half of the 16. So that would be 8. Day 5, you eat half of the 8, which would be 4. And then day 6, you eat half of the 4, which would mean you only ate 2 ounces of chips. So each day you're not eating like half of the original bag, you're eating half of what is left. So on like day 1, you eat 64 ounces. On day 2, if you only eat half of the remaining, that's only 32 ounces. On day 3, if you only eat half of the like new remaining, that's 16, and so on. So you can see each day it's decreasing by half, or you're like kind of dividing each number by 2 to get to the next number. So if we wanted to write a rule for this one, we could say f of x, and it would be the 128 that we start with, and then each day we're multiplying by a half over and over again. So like to go from 128 to 64, we multiplied by a half. To get from 64 to 32, we multiplied by a half. To get from 32 to 16, multiplied by 1/2, and to get from 16 to 8 multiplied by 1/2. You could see the pattern over and over again. So like on day 1, we multiplied by a half 1 time. On day 2, we multiplied by a half 2 times. On day 3, we multiplied by a half 3 times. And on day 4, we multiplied by a half 4 times. So we're multiplying by a half over and over again. And again, we have a way of writing multiplying by the same number over and over again. It's exponents. And since the like exponent is changing, like how many times we're multiplying by a half changes, it's going to be a variable exponent. So times 1/2 to the x power, and then same thing here, like our number of 1/2 that we are multiplying in matched the day number. So I'm just going to add a little arrow that says that x represents the day number. And then if we were to look at a graph of this one shouldn't be growing really quickly because each day we're eating like less and less chips. So it should be decreasing pretty quickly. So if we look at our graph, you can see it starts off pretty high and then it shoots down pretty quickly, but then it slows down at the end. So this is an example of exponential decay. So looking at our 2 rules, our 2 functions that we wrote, one was f of x equals 1 times 2 to the x power, and one was f of x equals 128 times 1/2 to the x power. The thing that makes these exponential functions is the fact that they are raised to a variable exponent. So that means that they will either increase or decrease exponentially because that exponent will change. Okay, a few things I want to point out on the graph. Really any graph, but it's especially handy for exponential functions, is the y-intercept is going to be where you're starting. So if we look at like our y-intercept on the first graph, it was at 0, 1, and that's because we started with $1 in our account. So the y-intercept is the starting point. And then if we look at the other graph, our y-intercept is 0, 128, and that's because we started with 128 ounces of chips. So that was our starting point again. So the y-intercept on, really, it's for like all functions, mostly every function, but they really come in handy for exponential functions. The y-intercept is going to be your starting point. Okay, and then the last thing I want to point out is that for exponential growth, your graph is going to go up and to the right, because we read graphs kind of like we read a book, like we would read left to right. And so like if it's going upward, it's growth or it's increasing. And then exponential decay would be down and to the right. So if you read the graph from left to right, it finishes going downward or decreasing. So that would be exponential decay. Okay, so moving down to example 1, determine if the following graphs represent exponential growth or decay. Under each graph, we're just going to write either growth or decay. In order to determine it, we just have to look at, is the graph finishing up and to the right for growth or down and to the right for decay? But we're always looking like to the right because we're just reading it from left to right just like you would a book. Okay, so example 1, the first one, if we look at our graph, so if we look we're reading it left to right, it finishes going down into the right. So since it's going down, that would be decay. Decay just means it's decreasing. And then if we look at the second graph, if we read it from left to right, it finishes going upward. So since it finishes going upward, that would be growth. Growth just means increasing. For the third one, if we follow the graph from left to right, it finishes going upward. Even though it's not like super steep, it does finish going upward. So since it's going up, that would be growth. And then for the last graph, if we read it from left to right, it finishes going downward. So that would be decay, or it's decreasing. So example 2 is to find the growth factor from the table and determine if the function is increasing or decreasing. So exponential functions are actually just like geometric sequences in that they both have a common factor or a common ratio that you multiply by to get to the next term. So our growth factor is going to be just like our common ratio from the geometric sequences. So if we look at our table and we kind of try to compare it back to the geometric sequences, that first row, all the x's, those are our inputs, but they're also just like our term numbers. And then the bottom row, the f of x, those are our outputs, but they're really just like the term values. So our growth factor we're going to find by figuring out what number I would have to multiply by like my f of x row to get to the next number. Okay, so if I focus in on that f of x row, I'm going from 2 to 6, I'm going from 6 to 18, and I'm going from 18 to 54. So if you can figure out what the growth factor is in your head, that's awesome. If you can't, you can always take one term and divide it by the previous term. So we can do 6 divided by 2, that's 3. So our growth factor is 3. You don't have to do the first two terms, you can do any two consecutive terms. If you did 18 divided by 6, that would be 3. Or even 54 divided by 18 would be 3 as well. So the growth factor is 3. You're multiplying by 3 each time to get to the next term or the next number in the output row. So our growth factor is 3. And then to determine whether it's increasing or decreasing for now, I just want to look at the table. So like, are our output values getting larger or getting smaller? We're going from 2 to 6 to 18 to 54. So those are definitely getting larger. So this is going to be increasing. So the growth factor is 3 and it's increasing. Okay, so moving on to the second table, same structure. All the x values are inputs or kind of like our term numbers if this was a sequence. All the f of x values are our outputs or like our term values. So we're going to determine the growth factor. So we're going from 81 to 27. We're going from 27 to 9, and we're going from 9 to 3. So we're not really growing, we're shrinking. And then if it's kind of hard to figure out what we're shrinking by, again, you can take one number and divide it by the number before it. So it doesn't have to be the first two. I'm actually going to take the last two and do 3 divided by 9. So 3 divided by 9. And then if you have a fraction, you want to reduce it. So remember, to reduce, you have to divide by a common number. So we can divide both by 3. So 3 divided by 3 would be 1, and then 9 divided by 3 would be 3. So that means that my growth rate is 1/3. So that's the number that I'm multiplying by each time to get to the next number. So times 1/3, times 1/3, times 1/3. And then if you recognize like from the very beginning that, you know, like 81 divided by 3 is 27, 27 divided by 3 is 9, 9 divided by 3 is 3, that's great. However, the growth rate is always what you're multiplying by. So even if you like identify that you need to divide by 3, you would just kind of want to convert that to multiplying by 1/3, because multiplying by 1/3 and dividing by 3 have the same outcome. So our growth factor is 1/3. And then to determine whether it's increasing or decreasing, we can look at how our values are changing. So we're going from 81 down to 27, down to 9, down to 3. So all those values are decreasing. Okay, so I want to compare our two tables as a whole before I move on to the next section. So on our first table for A, when we had a growth factor of 3, the function was increasing. It was getting larger. And for B, when we had a growth factor of 1/3, we were decreasing. So see if you can kind of like identify maybe like a pattern of like what made it increase for 3 and what made it decrease for 1/3. So moving on to the next section, we can also determine the growth factor of a function by finding the base of the exponential, because the base is going to be that number that's being multiplied by itself over and over and over again. So this is like standard form for an exponential, and you could see them in different forms, but for today we'll just use this one. It's f of x equals a times b to the x, where b is the base. So b is a base, and that's the number that can help you determine whether a function is increasing or decreasing. So if b is greater than 1, it would be increasing, just like we had like a base of 3 or a growth factor of 3 over here, and we had something that was increasing. And then if b is between 0 and 1, so like 1/2 or 1/3 like we had right here, the function is going to be decreasing. And the reason is because if I take a number that's like greater than 1 and I raise it to an exponent like I do with an exponential, it's going to get bigger and bigger and bigger. But if I take a number that's between 0 and 1, say like 1/2, and I raise it to an exponent, it's going to actually get smaller and smaller and smaller, surprisingly, because like if I did, you don't need to write this, this will just be a quick example that I erase, but if I do 1/2 times 1/2, that's 1/4, which is smaller than a half. And then if I multiply in another 1/2, that's 1/8, which is smaller than 1/8. So every time I multiply in a new half, it actually gives me a smaller outcome, which is what causes the decreasing. Okay, so moving on to example 3, state the growth factor of each function and determine if the function is increasing or decreasing. So the growth factor is going to be just whatever the base is. So in order to find the growth factor, we just need to find the base. So for A, it's f of x equals 3 times 0.4 to the x power. So the base is only the part of the equation that is being raised to the x. So in this case, the base would be just 0.4. It wouldn't be the 3, it wouldn't be 3 times 0.4. It's just the 0.4. So our growth factor is 0.4. Growth factor and base are the same thing. And then to determine if it's increasing or decreasing, we have to decide, is that number greater than 1 or is it between 0 and 1? It's between 0 and 1, so it would be decreasing. And then for b, it's g of x equals 1/2 times 5 to the x power. So same thing here, we need to identify the base. What number is being raised to the x power? It's a 5. So the base is the same thing as my growth factor, so it'd be 5. And then to determine if it's increasing or decreasing, we have to say, okay, is my growth factor greater than 1 or is it between 0 and 1? 5 is greater than 1, so it'd be increasing. For c, h of x equals 10 times 3/2 to the x power. The growth factor is going to be the same thing as the base, so we need to identify the base. It's just the number being raised to the x. It's 3/2. And then to determine if it's increasing or decreasing, we have to decide if 3/2 or 3/2 is greater than 1 or between 0 and 1. So not all fractions are between 0 and 1. If you have a number in the numerator that's bigger than the number in the denominator, if the number on top is bigger than the number on bottom, then your fraction has a value that's greater than 1. Or you could convert this to a fraction to a decimal by dividing 3 by 2, and that would be 1.5. So 1.5 is greater than 1, so this would be increasing because our growth factor is greater than 1. And then for d, k of x equals 3/5 to the x, so we have to find our base. our base is 3/5. That's the number being raised to the x power. So that's the same thing as our growth factor. And our growth factor is 3/5, which is a fraction, and it has the numerator smaller than the denominator, meaning the number on top is smaller than the bottom. So that means that that is less than 1. So if it's less than 1, it's like between 0 and 1, that would be decreasing. And then same thing here, if you felt more comfortable with it, you could convert this into like decimal form. So 3 divided by 5 would be 0.6. Whenever you convert to decimal form, you always do the number on top divided by the number on bottom. Okay, so moving on to example 4, this is the last example. Compare the functions and determine which function increases at the fastest rate. So which one has the highest growth rate? So I'm going to add a note there. So for which function increases at the highest rate, it just is asking which one has the highest. I'm going to shorten growth factor just to GF. So GF is growth factor. Okay, so for the first one, f of x, it's right here, f of x equals 0.1 times 6 to the x power. So this is just like the most recent example we did. We need to find the base. The base is going to be whatever our growth factor is. So our growth factor is 6. So we have that one. We have to find all three though, so we have to find all three to be able to compare and figure out which one is like the largest. So for f of x, the growth factor is 6. For g of x, we're given it in a table. And I'll go back up to the table examples really quick. So to find the growth factor from the table, that was when we had to figure out what do we need to multiply by to go from one like output value to the next output value. So if we look at my table, I'm just focusing on the g of x side. So 1, 4, 16, 48. So to go from 1 to 4, I know I need to multiply by 4. To go from 4 to 16, I need to multiply by 4. And then to go from 16 to 48, I need to multiply by, that is a typo. Ignore that, that's supposed to be a 64. But pretend it's a 64, I'll fix it for the notes by the time you guys print it. But to go from 16 to 64, I have to multiply by 4. Okay, so each time I'm multiplying by 4, sorry about that. Each time I'm multiplying by 4, so my growth factor is going to be 4 for that one. So growth factor for g of x is 4. So far f of x is winning. And then this one with the graph, we haven't really done or like shown the growth factor yet. I know we've looked at a graph, but in order to find the growth factor from the graph, we have to look at how the y values are changing. Because remember, like if we're looking at a table, all the numbers on this side are basically the equivalent of all the y values on a graph. So we'll focus on the y values. So from 3 to 9 to 27, to go from 3 to 9, I'm multiplying by 3. To go from 9 to 27, I'm multiplying by 3. So if each time I'm multiplying by 3, my growth factor is 3. So when you're looking at a graph, you just have to look at how are the y values changing. Okay, so now to figure out which one increases at the fastest rate, we have to figure out which one had the highest growth factor, which that was the first function, f of x. So we can say f of x increases at the fastest rate. So f of x increases at the fastest rate because it had the highest growth factor. So growth factor will always correspond with how quickly it's growing. The higher it is, the faster your function will grow.